So in this video, we're going to be working with the exponential function. Right? The exponential function, again, the general form is y equals to a b to the x, right? As you can see now, my second variable, my independent variable, is going to be the exponent of another coefficient, right? And it's telling you that a would not be 0, and that b, so the base of that exponent, is going to be greater than 0, and that b cannot equal to 1. In an exponential function, the base b is a constant, so it's a number. The exponent is a number that is not going to change. It doesn't matter. The number that's changing is the x. The exponent x is the independent variable with the domain, the set of real numbers. So that means that I can substitute to x any number that I want. We have two types of behavior. The exponential growth, so that means that it's growing, right? It's increasing while x is increasing, the y value is increasing. So this blue line represents exponential growth, right? Now the other one is exponential decay. So that means that while x is increasing, the value of y is decreasing, right? The exponential functions shown here are asymptotic to the x-axis. So that means that my x-axis is an asymptote. So that means that this graph is not going to intersect the x-axis, right? It's going to get very close, but it's never going to cross, right? So the exponential function, again, y is a times b to the x, where a is 0 and b is greater than 1, represent an exponential growth. So if b is greater than 1, it represents exponential growth. If b is between 0 and 1, remember again that we saw up here that b is going to be always positive. So if b is between 0 and 1, that is represent the exponential decay. Now, in either case, the y-intercept is 0, a, right? One of the properties of exponent is that anything to the 0 is going to be 1. So if b to the x to the 0 is 1, 1 times a is a, right? Now the domain, again, we saw that is all the real numbers, and the range, so the y values is going to be all numbers greater than 1, 0. So let's see this one. So I want to graph this, right? I want to graph this equation, right? So let's start by finding values, right? So if to x, y to the x, we can do like a small table here. So we can do a small table here, right? So I have x, f to the x, so y, and then x, y. So let's start by, let's say I want to substitute, let's start by substituting, say, -4. Right, so that means that I have y equals 2 to the -4. So that's 1 over 2 to the 4, so it's 1 over 16. So this is a very small number, so 0.0625. So again, 0.0625, and I have that point here, 0.0625. So that number is going to be something very close to here, right? Now I'm going to substitute -2. So I have y equals 2 to the -2. So this is 1. 2 to the square is 4. So this is 0.25. 0.25. So -2 and 0.25. Again, that number is very close, around somewhere around here, right? Now I'm going to substitute 0. So 2 to the 0. So 0. So 2 to the 0, again, that's a property, is 1. So I have the point 0, 1. So 0, 1 is this point here. Now I'm going to substitute 1. So 2 to the 1 equals 2. So 2, so 2. Now, alright, so now I'm going to substitute 2. And I'm going to do the same with 3. And let's go to 4. So 2 squared, 2 to the cube, 2 to the 4. So this is 4, 8, 16. So I have the point 2, 4. 3, 8, 4, 16. So 2, 4, 3, 8, and 4, 16. Right? And that's my graph. Remember again that the x-axis is an asymptote. So that means that this graph is not going to intersect the x-axis. And that's my graph. So the next one. So the next one, this one, let's approximate values. Again, we know that because I'm not multiplying that 3 to the x times 9. And it's again, we know that 3, 0, 1, if I substitute 3 to the 0, it's 1. Now, I also know that 3 to the 1, so 3 to the 1 is 3. So 3 is around here. Now, 3 squared equals 9. So 3 squared equals 9 is around here, right? Now 3 cubed is 27, so I don't have space there. It's a little bit, right? Again, because I'm not adding to the x or multiplying or adding anything here, my graph is going to be very close to my y-axis. Then it's going to start growing very quickly. From here, my next one is going to be all the way over there at 27. So it's going to be all the way there over there, somewhere around up here on number 27. And that's my graph, right? Let me put this other arrow here. Now, on this one, because my value up here, my value is, so because my value is less than 1, we know that it's decay. So we know that in this case, it's going to go the other way around, right? So in this case, let's see it, right? We can do the table. I'm going to do it by substituting. So let's start by substituting again. We know that 0, 1 is one of the points, right? Because 1 fourth to the 0, that's 1. 1/4 to the negative 1. Right? Remember that the exponent negative is going to have this, it's going to bring this to its reciprocal. So it's 4 over 1. 4 over 1 to the 1 is 4. So that means that this is negative 1/4. The same, so 1/4 to the negative 2. So this is, again, the negative is going to become positive by finding the reciprocal. So to the negative 2 is 16. So negative 2, 16. I don't think that I have any more space up here, right? So now to the 1, this is just 1/4. So it's going to be somewhere around here, right? Again, remember that the x-axis is an asymptote. So this graph is going something similar to this. Okay, now, in this case, now I'm multiplying times 5, right? Remember that we saw when we saw the, um, the formula, so a b to the x, that the y-intercept is 0, a. Why? Because if I substitute 0, so y equals 5, 2 times 1/2 times 0, so this is 5, this becomes 1, so it's just 5. So my y-intercept now is 0, 5. It's up here. Right? So again, let's substitute points. So let's start by substituting negative 2. So y equals 5 to 1/2 negative 2. The negative brings this to this reciprocal. So 2 squared. So 5 times 4 is 20. So negative 2 is up here. Right? Now if I substitute, let's say 1. So I have 5 times 1 to the 1. So it's 5/2. So this is approximately 2.5. So 2.5 is around here. Right? So my graph, again, is going to get close. It's going to start getting close to the x-axis down here. So something similar to this. Okay, so now we're going to be solving equation. For now, we're going to solve equation where I can change the base to be equal to each other. I can change one base, or I can change both bases. Now, later on, we're going to see another video where we can solve when we cannot find the base. So for example, 9, I know that 9 is the same as 3 squared, right? So I can substitute that 9, or I can change that 9 as 3 squared, right? As now I have the same basis, so 3 and minus 1, right? So 3 for n equals n minus 1, right? Now, because the bases are the same, that means that the only way that this equation is true is that the exponents are congruent. Again, if I have, let's say that if I raise 3 to the third, right, I have to raise another 3 over here to the third, so the exponent has to be the same, so the powers are the same. So right here, minus n on both sides, so this is 3n equals to negative 1, and now divided by 3, that means that n equals negative 1/3. Next one, again, here. Even though I know that 8 times 2 is 16, but I'm working with exponents, so I gotta take all of them to 2, right? So 2 to the third equals 8. Now 16 is 2 to the fourth, right? So I have the 2, negative 3k minus 9 equals 2 to the fourth. Again, my bases are the same, so that means that 3k minus 9 equals 4. Plus 9 on both sides, so negative 3k equals 13, and divided by negative 3 on both sides, so k equals negative 13 over 3. This one. So again, so 1, so 27, I can rewrite it as 3 to the negative 3, right? Why negative? Because I have this fraction and I want to convert it to a whole number, so 3 to the negative 3 to the negative 2m minus 2 equals 81, or 3 to the fourth. 81 is 3 to the fourth, so 3m. So 3 to 6m plus 6 equals to 3 to the 12m. Again, same basis, so exponents are congruent. 6m, so 6 equals 6m. Now I'm going to divide by 6, so m equals 1. Okay, now the exponential growth and decay, I can model it by using this function right here, where a to the t, so the amount after t periods, equals to the initial amount a times 1 plus r. That rate is going to be the rate of growth or decay, depending on the information, right? 1 plus r is going to be the growth factor or decay factor, depending on my values of b, right? And if it's given in percentages, we're going to change that to a decimal. So let's see an example here, right? So I have that says you invested 1,000. So we know that my initial value, so A was 1,000, $1,000, right? 1,000. In a saving account at the end of sixth grade, the account pays 5%. So we know that R is 5%, right? And we can rewrite this as 0.05. We're just moving that decimal point twice to the left. Okay. How much money will it in the account after 6 years? So we know that T is 6. So A of 6 equals 1,000 times 1 plus 0.05 times to the 6, right? Again, the formula was A to the T equals to A times 1 plus R to the T. Right, so we're just going to go to our calculator. So 1,000 is 1.05 to the 6. Remember that we're going to do that on the first, right? But we can do it directly in our calculator. So this equals to 1,340 with 10 cents. So at the end of 6 years, we're going to have 1,340 with 10 cents. Okay, so again, let's write a formula up here. So A of T equals A times 1 plus R to the T. So it says an investment of 75,000. So we know that A equals $75,000. It increased at a rate of 12 points. So R equals 20.5%. So moving the points 2 times. So this equal to 0.125. What is the value of the investment after 30 years? So T equals 30. So A of 30 equals to 75,000 times 1 plus 0.125 to the 30, right? So this equals to 75,000 times 1.125 to 30. So 75,000 is 1.25, 1.125 to the 30. This equals to 156,247 with 87 cents.